Here's the second part in the lecture on exponential and logarithms. I hope it ends on this one, but it might not. Let's do another derivative. As an example, let's consider y equals x to the 2x. And of course, x is greater than 0. You do not want to mess around with x being any real number and taking to powers, because with negative x's, that is, because you'll get a bunch of imaginary numbers. Anyways, what I'll do, since x is greater than 0, I know that I can rewrite y as equal to e to the natural log of x to the 2x. And then just like before, we're going to sneak that 2x down front. So y equals e to the 2x ln x. And in fact, after this particular example, I'm going to go directly from this spot to this spot, bypassing the explanation, because it's something that you should get comfortable with. You'll do it so often. So we take the derivative. You're going to get e to all that stuff, 2x ln of x, times the derivative of the exponent, 2x times ln of x. I'll use the product rule for that part. Of course, the first part, this part right here, all you have to do there is either leave it like that or put it back to x to the 2x. Your choice. I think I'll put it as x to the 2x. And you're not going to do anything with it for the rest of the problem, so just do the derivative of the rest of the stuff. So, the derivative of 2x is 2. So I have 2 ln of x plus 2x. This time, according to the product rule, I take the derivative of ln of x. So it times 1 over x. Perfectly fine way to leave your answer. I said I would only simplify if I'm going to use it in the next result. And I am. The reason why is on the graph, of y equals x to the 2x, there is a lowest point. Find that point. And this is a great example of a problem that connects the algebra with the geometry. All right, here's the function I was talking about. This is y equals x to the 2x. I mean to determine the lowest point on this graph, which is somewhere around here. Let me put a dot to indicate that. Also, you happen to notice that the lowest spot on the graph is also going to be a place where a horizontal tangent line occurs. In other words, I'm going to get the derivative equals to 0. So let me go back up to my derivative. My derivative was all this stuff. I am going to simplify it. I'm going to say dy over dx, since I am using it the next steps. What I'm going to do is I'll have 2 ln of x plus 2. Now you'll notice that this x and this x cancel each other out. Then, just to make life just a teensy bit easier on me, I'm going to take the 2 out front and have 2x to the 2x times ln of x plus 1. Set that equal to 0. So 2x to the 2x times ln of x plus 1 equals 0. Now, I know that x is positive, so all this stuff in the front is positive. I can therefore divide by that stuff. I know it's not 0. I don't care if it's positive. Actually, positive is not important. The fact that it's not 0 is important. So I'll divide both sides by that, and we'll end up with ln of x plus 1 equals 0. So ln of x equals -1. take e to both sides. E to the ln of x equals e to the negative 1. Well, the e and the ln cancel, and we end up with x equals e to the negative 1. All right, what is the y value associated with that? So this point here is e to the negative 1, comma, let me get the y value. Y equals x to the 2x. So let me plug in e to the negative 1, 2e to the negative 1. Well, if you know how exponents work, you know that you're supposed to take this exponent and multiply it to that exponent. And we end up with e to the negative 2e to the negative 1. Or if you want, e to the negative 2 divided by e. That seems a little easier. So our lowest point then is e to the negative 1 comma e to the negative 2 divided by e. And if you feel like getting those decimals, feel free. I'm just going to leave it at that. I found my lowest point. And the tangent line there is the horizontal line. The tangent line at x equal to e to the negative 1 is simply y equals e to the negative 2 slash e. So not so bad. It just, the numbers are not going to look that great, so you just got to be on the lookout for that. In calculus, you rarely get very good looking numbers. Another example, y equals cosine of x to the tangent of x. Now, it's understood when you're doing this problem that the only x's I'm going to work with are the x's that make cosine of x greater than 0. That way we have a real number that we're dealing with. But nonetheless, let's take the derivative of this and go through the same steps that I did before. First thing you want to do is rewrite y. You can do this in steps or not, but I'm going to do it all in one step. E to the tangent x ln cosine of x. That's a lot of stuff in the exponent, but then let's go take the derivative. dy over dx equals, you're going to repeat that thing, e to the tangent of x ln cosine of x times d over dx tangent of x times ln of cosine of x. Now that e to the tangent x ln, that is just the original function again, so that can be written as cosine of x. Fix my cosine. Cosine of x to the tangent of x times, now use the product rule. So the derivative of tangent is secant squared x, leave ln cosine of x alone, plus tangent of x times the derivative of ln cosine of x. So I'm going to get 1 over cosine of x, but I have to multiply by the derivative of the inner function, which was cosine of x. Now, you'll get better at this on the fly. I'm trying to take more steps than perhaps you will when you get comfortable. But the whole point of doing plenty of examples is that you do develop that comfort. So I have cosine of x to the tangent of x times, in parentheses now, secant squared of x times ln of cosine of x plus tangent of x times 1 over cosine of x times negative sine of x. And once again, that is perfectly fine. I make only the note that this back piece over here could have been simplified to negative tangent squared of x, but I'll leave it at that. Now let me go to more general exponential functions. If f of x equals b to the x, where b is greater than 0 and b does not equal 1, then we denote the inverse function, f inverse of x, as log base b of x. A lot of the times you'll be faced with an equation y equals log base b to the x. To get out of it, to invert it, you get x equals b to the y. And this goes both ways. Each one implies the other one. So it's what they call an if and only if proposition there. Let me take the derivative here of both sides. D over dx b to the y equals d over dx of x. As before, we have b to the y times y. Whoops. The derivative, the proper derivative of b to something is b to that thing times ln of b. So b to the y ln of b. But then I have times y prime, and that's equal to 1. Now y was equal to what? B to the y actually. B to the y was equal to x. So let me throw that in where b to the y was. I'll have x ln b times y prime equals 1. I'll divide by x ln b, and I'll get y prime equals 1 over x ln b. And so we now have a derivative rule for b to the x. Moving on. As an example, let's find the derivative of this one. Y equals log base 3 of x cubed plus 1. Let me bring that formula back. So the b in this case is 3. So I'm going to end up with dy over dx will equal 1 over, now remember, let's go back up here and view it, x ln b. So I'm going to have, what was my x here? X cubed plus 3, x cubed plus 1 times ln 3. But then I had things inside of there, so I'll take the derivative according to the chain rule of x cubed plus 1, and we end up with 1 over x cubed plus 1 ln 3 times 3x squared. For y equals log base 7 of radical x times secant of x, we have dy over dx equals 1 over, so we have square root of x times secant of x ln 7 times the derivative of radical x times secant of x. I'll use the product rule on that part. That equals 1 over radical x secant of x ln 7, increase the vinculum, times, according to the product rule, I take the square root of radical x first. We can use our new power rule, by the way. If you think of that thing as x to the 1/2, you can write it as 1/2 x to the negative 1/2 times secant of x. Let's face it, radical symbols have very limited use. I guess they're nice for display purposes, but they're really uncomfortable to work with algebraically. So, in fact, I would recommend you just forget about them altogether and go with changing all of those to powers. Anyways, the derivative of secant of x is secant of x times tangent of x. And I'll just live with that answer. I didn't talk about it much before. I sort of made mention of it when I did an earlier example, but I think I didn't quite make myself clear. Logarithmic differentiation. I think I'm going to do that now. Suppose you have a pretty horrible thing to take the derivative of. So I have x cubed minus 1 to the 4th power. the square root of 3x minus 1 all over x squared plus 1. Now if I want to take the derivative of this, you can do this according to a combination of rules, or we can do this business. Take the absolute value of both sides. Now I'm going to take the natural logarithm of both sides. Now, as I've mentioned before, I'm often leery of doing things like this because I didn't understand it before, but now, of course, I think I have a full understanding of this. I am then going to change this to the natural log of the absolute value of x cubed minus 1 to the fourth times the absolute value of the square root of 3x minus 1 all over the absolute value of x squared plus 1. Now you can argue about removing absolute values or not, depending on which of these are positive and which are not. I don't care about that. What I do care about is what I'm going to do next. I'm going to use the logarithm rules to break this up. So this is going to equal ln of the absolute value of x cubed minus 1 to the fourth plus ln the absolute value of 3x minus 1, the square root of 3x minus 1, minus ln of the absolute value of x squared plus 1. I'm going to take that 4 up front. So I'm going to have 4 ln the absolute value of x cubed minus 1. The power radical is 1/2 power, so I'm going to get plus 1/2 ln absolute value of 3x minus 1 minus ln. There's no good way to break up x squared plus 1 in terms of real numbers, so I'm stuck with that one. So what I have so far is I have ln absolute value of f of x equals 4 ln absolute value of x cubed minus 1 plus 1/2 ln absolute value of 3x minus 1 minus ln absolute value of x squared plus 1. For example, you can take the absolute value off the x squared plus 1. I don't care. All right, now I'm going to take the derivative of both sides. So the derivative of ln of absolute value of f of x is 1 over f of x times f prime of x. Notice how the absolute value disappeared, and all the rest of them are going to work that way. I'm at 4 over x cubed minus 1 times the derivative of x cubed minus 1. Next, I'm going to get 1 over 2 times 3x minus 1 times the derivative of 3x minus 1. Finally, I'll have negative 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. Now I'm going to simultaneously do a little simplifying and finish off the problem. I don't quite have the answer yet because of that guy. I have to multiply through everything by f of x. So f prime of x equals, so f of x to begin with. The first piece, if I simplify, I'll get 12x squared over x cubed minus 1. And then I'm going to have 3 over 2 plus 3 over 2 times 3x minus 1. And the last piece, I'll have minus 2x over x squared plus 1. So there you go. Horrible looking derivative, but imagine how it would have been. The reason I put all those absolute values in there was to tell you why it was possible to take these derivatives and to break things up into pieces. Because typically, when you break a natural logarithm up into pieces, you change the amount, the numbers that the x's can be. You, in effect, change the domain. But not with this, because after you take the derivatives, you get the same thing you would have gotten anyways. I challenge you to completely ignore any absolute values and just do the derivative using logarithmic differentiation. I have f of x equals x to the 8th cosine cubed x all over, let's say the cubed root of x minus 1. So then what you'll do is you'll do ln of f of x equals ln of x to the 8th cosine cubed of x over the cubed root of x minus 1. Now I want to break that up according to the logarithm rules and just completely ignore signs of any kind. I'm going to act like there's absolute values there even though they're not. See if I'm going to do this all in one step. I want you to look at it, pause it, whatever you need to do. But here's what I get. 8 ln x plus 3 ln cosine of x minus 1/3 ln x minus 1. Now take the derivative of both sides. So I end up with f prime of x over f of x equals 8 over x plus 3 over cosine of x times negative sine of x minus 1 over 3 times x minus 1. The derivative of x minus 1 is 1. So let's see if you can follow this then. F prime of x, f of x was all the original stuff. So it was x to the 8th cosine cubed of x over the cubed root of x minus 1. And that's times 8 over x minus 3 tangent of x. See if you can follow that one. Minus 1 over 3 times x minus 1. So there you go. I think I've completed the lecture topics that I want to use for exponential and logarithm functions.